Hi there, this is Advanced SQL and our discussion of types in PostgreSQL. So what we're doing now is concerning a real strength, I would say, of the PostgreSQL system in that it provides a library and operations to directly operate with geometric objects, geometric entities inside a query. So we can have tables in which cells are carrying lines and boxes and circles and polygons and so on. And we have a built-in function library of operations that will query these geometric objects for their intersections, for their spatial relationships, for their areas, for their diameters and so on, for their distances and so on. This can make some really powerful stuff, a really powerful fundament on which you can build applications that rely on geometric primitives. All right, so before we can do that, we would of course need to construct such geometric objects inside PostgreSQL. And here you can see a selection of geometric objects that would be supported inside the system. We can of course talk about points P here, and if you would like to construct such a point inside a query, we could use the textual syntax that you see here between quotes, just the coordinates, the 2D coordinates of the point in the 2D plane, enclosed in parentheses, or we could use the constructor syntax that uses the keyword or the constructor word point here to construct the same geometric object. Actually, I'm a fan of this explicit constructor form of syntax when it comes to the construction of geometric objects, because as you can see, when you construct more complex geometric objects, you end up with mountains of nested parentheses that describe points that are contained in larger geometric objects and so on. So I would recommend to stick with the constructor-based construction syntax if you can, if you prefer. So this is how we would construct 2D points. We could construct line segments, so lines that start and end at given points, and that would be the line segment syntax below here. All right, we could have lines that just go through points P1 and P2 and then extend indefinitely further, just as lines are doing, and that would be the syntax to construct such lines. We could construct boxes by specifying the two corner points of such a box, P1 and P2 here, and that would be the constructor syntax to do that, just that. We would have syntax to describe open paths, so just collection of points that are connected if they're adjacent in this textual syntax, using the square brackets, as you can see. All right, so this would be an open path. It's not required that P1 and Pn, the final point of this path, are indeed the same point. Okay, so it could be just an arbitrary path in the 2D plane. Okay, closed paths or polygons are described by this syntax with the open parentheses here, and you see this is the polygon, a triangle of 3 points that I've described here. And the starting and the ending point of such a polygon are indeed identical. All right, and last but not least, we could specify circles which have a center point P, which I could, of course, construct using any of the two methods I've described here on the left, and then such circles already also equipped with a radius R that I'm specifying, and that would completely define a circle in the 2D plane here. As you can see, for all of these constructor-based syntaxes, you will also find textual syntaxes, string literal-based syntaxes. I'm not listing all of these here. You can easily check the very extensive PostgreSQL docs to see how line segments, circles, and so on could be specified alternatively in textual syntax. I told you, so I'm a big fan of the constructor-based syntax here. Together with these geometric objects, we get a vast collection of operations on these objects, so that queries can inspect objects and construct new objects from old given objects. So that's what you would find here. You would find operations that can translate objects in a 2D plane. So shift a particular object, a circle say, and move it by a particular vector and shift it in the plane. We could scale and return or rotate objects. We can compute length and circumferences of objects. We can compute the distance between objects, whether two objects intersect, how they are located relatively in the 2D plane, whether one contains the other, and so on. These would be query operations that inspect details about a particular given geometric object, like the height and the width of boxes, or the area of a circle or of a box. Computing a bounding box around a polygon, for example, so that I have an enclosing box-like object that contains all the points of a polygon. We could compute the centimeters, the center and diameters of circles. We can query whether the path is closed, how many points it contains, and so on and so on. The list goes on. This really is only an excerpt of what is possible and available inside PostgreSQL. The support is really extensive. Okay, what will come up now and then is that once you're given a point P, you would like to inquire about its x and y coordinates in the 2D plane. And PostgreSQL uses this particular syntax, this subscript, array subscript syntax, to check for the x and for the y coordinate of a point in the 2D plane. So what could we do with that? So let's switch over to the editor and let's check. So this would be a nice simple example that uses the Monte Carlo method of approximating P, the value of P. Okay. And how would we do that? Well, we would simply check whether a randomly generated point, you can see that I'm using the point constructor syntax here, whether a randomly generated point is contained within a well-defined circle that we are placing in the 2D plane. So this is the predicate that just checks whether this particular point is contained in this circle. So let's see what circle I'm actually describing here. So we are in the 2D plane. All right, and the circle I was describing there is located at 0.5, 0.5. Okay, so this will be the center of this circle, and the radius of that circle would be 0.5. So let's see whether I can draw this circle. Please forgive me. All right. Okay, so this is the circle that we had constructed, and we were now placing random points in this 2D plane, and the random points are located in this square. So the square has borders at 1, so this would be the square. So of course the square should touch the perimeter of the circle here. And then what we would do, what the Monte Carlo method would do, it would just generate random points and check whether this particular point is contained in a circle. Oh, it's not. Okay. Oh, this point is contained. This is contained. This not. It's contained. Contained. Not contained. Okay. So we would just generate random points, check whether they are contained in the circle, and from that estimate the value of pi. So because there is a particular chance that a point will actually be contained in the circle here. Okay, and this is just what is implemented in this tiny query. So the random point generation will make sure that the points are actually in the square with width and height 1, because the random values generated here are between 0 and 1. Very convenient. This is the circle we had described in the 2D plane. This is the predicate a built-in predicate that is checking the containment of the point inside the circle. All right, and what we are doing is we are just generating lots of these random points. As you can see, I've defined the PSQL variable here, the n here. It's 10,000. So what this generate series will do, it will just generate 10,000 integers from 1 to 10,000. But we don't care about the integers. So let's use this particular row variable here that indicates that we are just not interested in the values themselves. We are interested in the repetition of generating random points and then checking containment. And for all of the points that are actually that fall into the circle, we will just count them. We will just count them using this count star here. And of course, scale this by n. All right. And then do some tiny computation here. We multiply by 4 to arrive at the true value of pi, because what we're actually computing here is the 1/4 of pi, and why this is the case is explained in the file I'm providing. We are not looking into this here, but we are just interested in geometric object construction and of course the Boolean predicate that we're using here to check containment. So let's just try that. Let's try that and compute the value of pi, or estimate it using the Monte Carlo method. Okay, that was fast. So it's 3.1444 by this approximation, which is not too shabby already. So if we would invest more time, generate more random points, we would probably increase our precision here. So let's use a larger n value and generate more points. Okay, so that looks like a reasonable approximation of pi already. Okay, very easily and very directly achieved using just the geometric operations and objects that are available inside queries in PostgreSQL. Okay, so let's look at a little larger example to close off our discussion of these geometric objects. So I'm looking at this tiny use case. I would call it a shape scanner. So what we are trying to do is inside the 2D plane, we are placing a polygon of unknown shape, some polygon that we would try to analyze or would try to discover. And what we will do is we will scan the area of the 2D plane in which that shape is located. So we will scan the area from left to right here. So x would advance. And for each of the x coordinates, we would check where we can find the lower border of the shape or the upper border of the shape. So we would shoot rays, you could say, from the top down to the shape and from the bottom up to the shape, and then would record where we hit the border of the shape. And we would do this for all the x coordinates that we let advance from left to right here. The result of the scan would probably be something like this. So we would, for each of the x coordinate, we would record where we hit the shape from the bottom, and we would record where we hit the shape from the top. This would be the output of our shape scanner, and we could pass this to some plotting or drawing program, which would then draw an approximate drawing of the formerly unknown shape that we have placed in the 2D plane. All right, so let's see whether we can implement this using our geometric primitives inside PostgreSQL. So this is what I'm doing here in this sample file. All right, let's see, how shall we start? This is a table of unknown shapes that I've prepared. Okay, so these are polygons constructed using the polygon geometric object syntax available in PostgreSQL. There's many of such syntax available. So one would be using the textual representation of polygons, which is just a comma-separated list of points enclosed in round parentheses here. So that would be a polygon, and a polygon is a closed shape. So the implicit edge from two 0 to back to 0, 0, the starting point, is included in this closed polygon path. All right. I can also convert other geometric objects into polygons. So, for example, I could just place 2 points in the plane, then based on these points generate a box, all right, and then convert this box into a polygon of 4 sides, obviously. So that would be another method to construct a polygon in PostgreSQL. I could also construct a circle centered at point 0, 0 with radius 1, and then convert that circle back into a polygon. By default, the circle would be approximated by, I think, 12 edges, but I think I could provide a parameter here that would lead to more coarse or more finer approximations of the circle's shape before we convert it into a polygon. All right, and here's another textual specification of a polygon, the polygon with shape with ID 4, that has some more complex shape that is not immediately recognizable to me. This thing, I guess, would specify a triangle. This is also suggested by the comment. Okay, so this would be my collection of shapes that I would like to explore with my shape scanner. Okay, so to do that, I would first have to construct the bounding box. The bounding box around these shapes, because the bounding box would be very helpful to see where my x and y coordinates are and how the scanning should go. So if this is my unknown shape and I could construct a bounding box of this shape, I would know the x values that I have to scan, and I would have an idea of the y values that I could use to shoot the rays from the top and to the bottom. Okay, so that's what we are going to do next here. So given the shapes, we would construct the bounding boxes and query some of the vital coordinates of the bounding boxes. So we would iterate over all the shapes, the 4 shapes we have just defined. Then for each of the shape, construct its bounding box, which is just done by inserting the polygon s.shape as a polygon inside this box constructor call, which would construct a box that contains all the points of the polygon. It would be a bounding box for the polygon. And for this particular box, we would record its center. We would also record its width and its height. Okay. And then, of course, take note for which of these shapes we have recorded this bounding box information. All right, this is vital information. So we've got the shapes and we got the table of bounding boxes, which records center, width, and height for each of the shapes. This is enough preparation to actually perform the scanning. So let's do that. Let's do the scanning. Here's the scanner. As is usual with SQL, even cool stuff only occupies like 5 to 10 lines. Okay, so what are we doing here? We are iterating over all the shapes. So we will scan all the given shapes at once, and also check the bounding boxes B for the particular shape. You can see the where clause here, the join makes sure that we are associating the correct bounding box with the correct shapes. All right, once we've got the bounding box B of a shape, we can enumerate the x and y coordinates in the 2D plane that we want to use for the scanning. So you can see I'm using to generate series calls here to generate x and y coordinates. Okay, so the x coordinate would start left of the center. Okay, so this is half the width left of the center and would extend half the width right to the center. Okay, so that would be the range of x values that we are considering. And we consider them in a particular step with a resolution that I've defined above. I can show you in a minute. Okay, the same is being done for the y coordinates. All right, so we start at the center, below the center, half a width below the center, extend that scanning to have a width above the center. Okay. And of course, also will do that in the given resolution. And these are the XY coordinates that I'm using for my scanning process. Okay. And then I would just check whether the generated point at coordinates XY, so this is constructor syntax for geometric objects, is contained in the unknown shape. And the is contained in the Boolean predicate that we are requiring here is just a provided built-in function by PostgreSQL. All right. Okay. So any point that can qualify, any point that is actually touching or is inside the shape would pass this particular predicate. All right. So for each of the shape and each of the x coordinates that we are considering here, we would record for which shape we have done the particular scanning, and we would record the minimum and the maximum y value that has been recorded for this particular x coordinate. Going back to our graphics here, considering a particular x coordinate, this for example, okay, we would take note of the minimum and the maximum y value that has been found. And that would be the scan result for this particular x coordinate. It would be the scan result that corresponds to this and probably the middle arrow of this that is highlighted now here on the slide. These would be the minimum and the maximum scan values that we have seen for this particular x coordinate. And we would record these as a result of our scanning process. All right. This is what's being done here. That's all. To have an ordered output, we would organize our output by shape and then by x coordinates so that we see the scan result being outputted in a scan from left to right. That's all about it. Okay. So you have seen this variable value resolution here. And it's set to 0.01, but any value would do that you would like to put here. It will determine how accurately we are scanning the shape in the 2D plane. All right. We have many shapes to scan here. For the output, I would just select a particular shape, namely shape 1, and the result of the scanning I will later write using a copy command, a SQL copy command, into a particular CSV file, which is nice because I can then read this CSV file to check whether the scanning delivered some sensible result for us. Okay, so let's see this final step. So we know all of this stuff already. So not much to be done. So from all the traces that we have just generated, trace is the CTE name that we have introduced here. Okay. So from all the traces, we will only select that one trace that we are currently interested in, the value bound to variable shape. I think it was 1 defined above at the file. And for the scanned x coordinates, we will just print the x coordinate and then also output the bottom and top scan result values that we have recorded. This should be enough information for a graphical plotter, for some drawing program to really render the shape for us. And that's what we're going to do. The output of this tracing for the selected shape will be written to a CSV file. The CSV file is located at a path I've defined above in the file, and please output that tabular data into the CSV file in CSV format. That makes sense. We have seen the copy to SQL command before. When we copy the byte array blob data, the WAV files from our GLaDOS program into the file system for later rendering by the audio program. Now we are not passing the data directly to a program or to BaseVN 6040 coder, but we are saving it into a CSV file. So let's do that. So lots of preparation. Let's copy and mark the whole thing here. down to the bottom. Okay, and then scan, go. Okay, so 201 lines have been copied to the CSV file. Let's check. This is directory into which the CSV file has been written. Contour CSV, May 5th. Yes, this is the actual, the current date. This is CSV file has just been written. Let's have a quick look inside the file. Okay, so yeah, that looks like a typical CSV file. Each of the lines of this CSV file has 3 entries as defined by the query that we were outputting. The X coordinate increased in the resolution steps that we have defined, and the minimum and the maximum Y value that has been recorded at this particular X coordinate. Okay, so this is the output of our scanning process. And because nobody can interpret this CSV data, I've written a very quick gnuplot script that can convert this CSV data into something that we can actually look at. So this gnuplot script will read the CSV file and then render the bottom and the top trace that we've recorded during the scanning to visualize this for us. So let's do that. That's quick. Let me get my web browser, which contains the rendering. Okay. It appears we have rendered the shape that looks like a triangle. All right. So here's the bottom trace. Here's the top trace. Both have been properly scanned by our scanning program. So one more test. Let's scan the circle. Okay, so the circle is shape 3. Okay, so let's define shape 3 here. Okay, from now on, the shape variable is of value 3. And now we are repeating the query out with the same file. Okay. A new contour file has been written. Nice. Gnuplot scanner. This is the circle. As I told you, the PostgreSQL conversion from circle to box has used 12 edges to approximate the shape of the circle, and or the ellipse. One should know it's a circle actually. Yes, given the coordinates, it's a circle. Okay, so this is what the scanner could detect. All right, works perfectly. So this is one demonstration of the use of the geometric objects and the geometric operations over the geometric types available in PostgreSQL. And I think that's quite remarkable support. But it's getting even richer. And if you stay tuned, you will learn more, even more about more cool types that are available in PostgreSQL. I hope I can see you again then. Until then, bye.